All right. Hi, I'm Arda, and I'm with Jeremiah and Rhoda, and we're going to illustrate radioactive decay using water bags. In this bag here, this is a water bag, and this is supposed to represent technetium-99, and this bag contains soap and is supposed to represent iodine-131. The radioactive decay equation is as follows, where we have A representing activity, so we have activity at time t equal to the initial activity times e to the lambda times time. And when we break it down a little further, each of our components represents a different part of this equation, where the initial liquid, the amount of liquid that's in the bag, is represented by A naught. The amount of liquid at time t represented by A of t. Then we have half-life, which is part of lambda, which is represented by the viscosity of the liquid in the bags, and then we have time. All right, so the water bags that we're using for this illustration both have an identical size hole cut in each one. The amount of liquid that's in the bag represents the radioactivity, and then the rate at which the liquid flows out of the bag represents the half-life. And here in a second, we will be flipping and illustrating this radioactive decay. All right, 3, 2, 1, go. Okay. So, Jeremiah, what do we have here?
This is sodium pertechnetate. It's used for imaging. Technologists have to calculate this dose daily because of its short half-life of 6 hours.
Okay, that makes a lot of sense. So Rhoda, what do we have here?
We got iodine-131. It's used for the treatment of thyroid cancer, and it has a half-life of 8 days. This makes it convenient for technologists to prepare doses, but it may leave patients with unwanted radioactivity after.
Okay, and we can see the sodium pertechnetate is already completed decaying while we're nowhere even close with the iodine-131. Thank you, Jeremiah and Rhoda, for that wonderful performance. And now we will be demonstrating a real-world application of this equation.
Okay, so we're going to be using the same decay equation, but for this example, we're going to pretend we're going to have 20 millicuries of a vial of sodium pertechnetate and iodine-131 and see their radioactivity after 10 hours. So for the sodium pertechnetate, we're going to use the same equation, plug in the 20 millicuries and the 10 hours, but for the half-life, we're going to put 6.06 hours. And if we solve this equation, we get a value of 6.37 millicuries. But for the value for the iodine-131, we put in a value of 192 hours for its half-life, and we get a value of 19.2 millicuries.
To summarize, it is very important that we learn this equation and know how to use it in real world for several reasons, such as calculating daily doses, transporting these doses, or even just as hazardous waste decays after we use it. Thank you, and remember, time, distance, and shielding.